like 10 or 20 minutes so that I don't build up a video for 1 hour and it becomes difficult to upload it. So I'll let you know when I stop the presentation and I'll start again a couple of minutes after that. Okay. So now let us just quickly review what is a binary search tree. So a binary search tree is nothing but is a binary tree wherein when you consider the data for the nodes, for any internal node, its data is going to be greater than or equal to the data of its left child and less than or equal to the data of its right child. So in this sense, for any internal node, its data is going to be greater than or equal to everything in its left subtree and less than or equal to everything in its right subtree. So that's what a binary search tree is. So now we also saw in the earlier module the tree traversals algorithms, the pre-order, post-order, in-order traversal algorithms. And there is a property relating the in-order traversal and binary search tree, that is, if you do an in-order traversal of a binary search tree, you are going to be able to list the data, which we call as the keys, in a sorted order. So let us look at an example and we'll come back to this kind of proof. So this is a binary search tree and I do an in-order traversal of this. So in-order traversal, the rule is you visit everything in the left subtree, followed by the root, followed by everything in the right subtree. So you start with the root, but you don't print the root first, go to its left subtree. For the left subtree, node 1 is the root, but again you don't print the root right away, go to its left subtree, which is just node 0, that is the root, there's no left subtree, so we'll just print the root, so which is node 0 and its data, which is 12. So done with the left child, then go to the root. So this is the root node 1 with data 19, so print it now. Go to its right subtree. The right subtree, the root is 2, so check if some left subtree exists. There's nothing, there's no left subtree, so now print the root, which is 2 and the data is 22. Then go to the right subtree, which is 3 and the data is 25. Then you're done with the left subtree, go to the root, which is 4, the data is 25. Now go to the right subtree. You don't print the root right away, go to its left subtree, which is node 5. There's no left subtree for node 5, so print node 5 and data 27. Go to its right subtree, node 6, data 27. Then go to the root, which is 7, data 30. Then go to the right subtree, which is node 8, and there's no left subtree, so print the root node 8 and its data 33, and then 9 and 37. So we just did an in-order traversal of this binary search tree, and you can notice the data is kind of listed in the sorted order. So that is the property. When you do an in-order traversal of a binary search tree, the data of the nodes that you list out will be in the sorted order. Okay. So kind of we can prove this as a theorem and prove property. So let us say we have two keys in general, some k1 and k2 in the binary search tree, such that the data for the key value k1 is less than k2. So if that is the case, how can these two keys, the corresponding nodes, be arranged in a binary search tree? Now there are three possible ways that k1 and k2 can be located in this binary search tree. Now since k1 is less than k2, one way is k2 is, say, the root of some subtree. It could be the root itself for the overall tree or root of some subtree, and k1 is in the left subtree of k2, because again from binary search tree point of view, the data for any root node should be greater than or equal to everything to its left subtree. So k1 is less than k2, so k1 could be part of the left subtree of k2. So that's one possibility. The other possibility is k1 could be the root and k2 could be in the right subtree, because again for a binary search tree, the data for the root node could be greater than or equal to the data of everything in its rights. Sorry, the data of the root node is less than or equal to everything in the right subtree, right? So K1 is less than K2, so K2 could be in the right subtree of K1. That's one way. The other way is there could be a common root node like K3, and K1 is into the left of K3 because K1 is less than K2, K1 has to be the left and K2 has to be the right, and K3 is a common. So again, so K3 is greater than K1 but less than K2, but still K1 is less than K2. So either way, no. So these are three possibilities. K1 and K2 can be located in a binary search tree, satisfying this condition that K1 is less than K2. So now when you do a in-order traversal of each of these binary search trees, what will happen? So let us do this one. So when you do an in-order traversal of this binary search tree, you start with the root but don't list the root, go to the left subtree, go to everything to its left. So K1 is the first data node that will be printed. Then you print the root, everything, go to K3, print K3, then go to the right and print K2. So this way K1 is listed first, followed by K2. So that is in the sorted order. Similarly, if you do an in-order traversal on this subtree, you start with the root but don't print the root, go to the left subtree, so go everything to the left, so you print K1, then you go and print the root. So you first print K1 followed by K2. Similarly here, you start with the root, don't print the root, go to left subtree, there's nothing in this example, so print the root K1, then go to the right subtree and print K2. So again K1 is printed before K2. So in all these three binary search trees, you will have K1 printed before K2 when you do an in-order traversal. So this is how you can prove this property that an in-order traversal of a binary search tree will always list the data nodes in the sorted order. Okay.